Everyone, welcome to our presentation. Today I will introduce an innovation study on math, a multi-region first learning framework for each feature selection. The study designed an efficient framework to optimize spatial, and temporal feature of each signals, providing a novel solution for classification tasks in Brain computer interface (BCI). I will walk you through the research background, challenges, methods, and the contributions of this work. First, introduction. BCI is a cutting-edge technology that connects the brain to electronic device, widely applied in areas like rehabilitation, robotics. Each signal as a common type of brainwave data has become crucial in BCI research due to their low-cost portability and non-invasiveness. Particularly in motor imaginary tasks, user generates easy signals by imaging movements which can then be used to classify user intent. However, e-signals are high subject and exhibit inter-subject and intra-subject variability, making feature extraction significant challenges. This complexity demands a dynamic and adaptive framework for each feature selection. The development of the math framework addresses the challenges of each data analysis and feature selection. Each signals are highly variable, making feature extraction complex, where traditional machine learning lacks adaptability for such data. Reinforcement learning offers dynamic optimization, but a single agent approach is for to capture the synergy between spatial and temporal feature. Multi-agent systems handle multi-object tasks but face collaboration in efficiency such as credit assignments and free rate issues. Must leverage multi-agent I/O to enable balanced, efficient, and collaborative feature selection for easy signals. The math framework introduced an environmental multi-agent reinforcement learning approach for collaborative optimizing of spatial and temporal feature. It incorporates a counterfactual baseline to address credit assignments and prevent free reader behaviors. Additionally, collaboration-based evolutionary search enhance training robust by dynamic optimizing hyperparameters. Two methods. The math framework consists of three main steps. First, feature extraction. EGNet is used to extract feature from each signals via spatial and temporal convolutionary layers, generating a low-dimension feature map F0. The feature map contains two dimensions: spatial information and temporal information, forming the foundation for subsequent feature selection. Second, feature selection. Two agents collaboratively optimize feature in different domains. The spectral agent focusing on selecting feature in spatial domain. The temporal agent optimize features in the temporal domains. The reinforcement learning from models the feature selection problem as a decentralized partially observable Markov decision process, enabling collaboration between agents. Third, classification tasks. The final feature maps FT containing selected key features is generated by math. Global average point is applied to the selected features map to produce a global feature vector, which is fed into a classifier to predict the MI categories. The math framework uses multi-agent reinforcement learning to optimize each feature selection. Two agents interact in a shared environment, observing local state and deciding to select or reject a feature based on their policy. Rewards are calculated by covering baseline loss L-base with the loss after selection LT. Guideline strategy refinement or cumulative rewards, incorporates a discount factor to balance immediate and future gains. The dynamic structure enables efficient collaborative feature selection and improvements easy classification performance. The centralized created estimates the joint action value function QSTAT use global information to guide aging towards collaborative strategies, avoiding local optimal and improving efficiency. The counterfactual baseline solving the created assessment problem by codifying each agent's marginal contribution, comparing current action with alternatives to ensure fair contributions and prevent free riders behaviors. The cooperative policy leverage shared rewards and counterfactual baseline to align aging strategy with global objectives, fostering implicit collaboration and balancing spatial, spectral, and temporal feature selection for better performance. Must use evolutionary search to optimize hyperparameters by maintaining multiple sites, evaluating performance, and applying local adjustments to top performing configuration. This balance exploration and refinement, improving training stability and performance. Must selected the KMI related feature to generate a final feature map FT, applying global averaging polling to create a global feature vector and use it in a classifier to for MI prediction. It ensure efficient and accurate EEG classification. That's all for my part. Next part will be given by Chung Liang. Thank you.
Thank you, Yaxing. I'm Gabriel. Now I'm going to present the data description and experiments. The study utilized two EEG datasets, a BCI competition 42A and the KUMI dataset. The BCI dataset included 9 subjects performing 4 motor imagery tasks, recorded with 22 electrodes at 250 Hz. The KUMI, a larger dataset with 54 subjects performing 2 MI tasks, was recorded at 1000 Hz, downsampled to 250 Hz for consistency. Each trial consisted of 4.5 seconds of EEG data preprocessed with a bandpass filter and exponential moving standardization. This ensured uniformity across datasets. Two scenarios were designed to evaluate the Mars framework, a subject-dependent and subject-independent. In the subject-dependent setup, training and testing data came from different sessions of the same subject. For the subject-independent setup, the leave one subject out method was used. The study compared mass against baseline models without feature selection, single-agent reinforcement learning for feature selection, and sequential combinations of single-agent RL frameworks for multi-objective selection. The results. Mars achieved the highest classification accuracy across scenarios, including a 72.13% in the BCI dataset and 66.74% in the KUMI dataset for subject-dependent setups. In subject-independent setups, it reached a statistically significant 60.08% mean accuracy on the BCI dataset. Statistical analysis confirmed significant improvements over all benchmarks. Other methods, such as the single-agent RL, showed improvements but did not outperform Mars. Additional tests with deep convolutional net, sync EEG net, and ATC net demonstrated Mars' versatility. It consistently improved results, highlighting its adaptability to different backbone models. This supports the framework's broader potential in EEG signal analysis and confirms its effectiveness in multi-objective feature selection tasks. Now I'll pass to Yongyang for the discussion.
Okay, so hi, I'm Yu Yang, and I'm going to present for the last part, which is about the discussion, the conclusion, and also somehow the evolution of this paper. So in section 5, we're going to discuss about the discussion part. So in this paper, the researchers point out few things about the Mars structure. The first thing is about the importance of spatial spectral agent. Because in this table, we can see that we are using single agent. One is using temporal, another is using spatial spectral agent. We can see that they have similar accuracy, mean accuracy, in the subject-dependent scenario which is using the BCI dataset. It also comes the same when they are using the KUMI dataset, and also in the subject-independent scenario. So we can say that the spatial spectral features are as important as the temporal features. The second thing is about the effectiveness of collaboration between agents. So that we can see in the different scenarios here, the blue line is about the mass structure, and it has a significantly higher learning curve than it. So we can say that mass shows an extraordinary growth on the learning curves of cumulative rewards. And besides of pointing out this, the researchers also thinking that why it happens, and by the discussion, they mentioned that the centralized critic contributed to this. So that with this centralized critic, it brings collaboration, but not just only putting two agents together to work. It has some kind of collaboration work in it. So following on, we can see the effectiveness of cooperative behaviors. So in the multiple single agent scenario, which is we are using both agents, but we don't have the centralized critic, the count of free riders is quite many. But by using the mass structure, it significantly lower the count of free rider compared to the multiple single agent scenario. And at last, the researchers also pointed out other things, such as the compatibility with other backbone models, because with the mass structure, besides using EEG net, because you also use the deep convolution net, sync EEG net, and also the ATC net. Other than that, it also has a potential to use in the real world implementations, because as here, even we are using the deep convolutional net, we can see that the inference time per shell will be 0.99 ms. But according to other papers, as long as this time is lower than is within 1 to 2 seconds, then it won't cause significant delays, and it is applicable to the practice. So next we are going to go into the section 6, which is about the conclusion. So about this paper, whether you are comparing with the single agent methods or the multiple single agent methods, we can say that the mass structure outperforms them by the results just now. And also we can see that the novel application and adaptation of such methods to EEG-based BCI tests actually fill the existing research gap. It's like they propose a new thing, and it significantly has the performance improve. And no other researchers did it before. In the future work, the researchers suggest that either we can increase the number of agents used in this structure, or we integrate the transformer-based models into the framework, because this is some kind of models that are the trend and shows a better performance than other models. So basically, it's like to extend the use of mass structure. So at last, we get into the evaluation part. So for us, there are 3 points that we can say that it's some kind of novelty that brings out from this paper. The first is about the spatial the collaboration. So that with the assistance of centralized critic, it's not just that in this structure, we put a spatial spectral agent and then a temporal agent. It makes some kind of collaboration between them. And the next thing is about the improvement. It's like it's not just introducing a new structure, but it did improve its performance by this structure. And the third thing is about the compatibility. Because the whole mask structure is about the feature extraction part. And for the other models like the EEG-net, the AIT306 also the deconvolution net, they are about getting the input, the features as input and do their things. So it's quite independent for these two parts. Hence, by using the mask structure, you still can integrate it with the other deep learning like deep convolutional net and such other models. So that's all the introduction of this paper. Thanks for listening to our presentation.